Alright guys, now this is the third one, and if I stressed the devil's in the details before, this one's even more complicated, so be very careful. So now it says, imagine the tiger and the gazelle are sliding on a frictionless surface at the velocity found in problem 1. Okay, we got that. After a short distance, the gazelle and the tiger reach a rough surface that has a coefficient of friction of this value right here with animal fur. So okay, so it's going to cause them to slow down and eventually come to a stop. How much work, so we're looking for work, must be done by the friction to bring the gazelle and a tiger to a stop? Now, this is where we have to do a couple tries, guys. Now, I can just give you guys the answers because I know them, and you start becoming things become intuitive. But let's take a look first. Well, what we could do is this. Remember that F. Let's draw the free body diagram. That's a great idea. So let's say here is our two animals stuck together. I'm just going to draw it as a box, and here they are on a surface. Okay. So we're asked for how much work is done by friction to bring them to a stop. Well, what you should see is that this object, it has a FG going down. Once again, these are my two animals, this blue box. And then you have a normal force going up. And then I always put it going off to the left, but you've got a force of friction slowing us down. Now, what we should see, and what you guys should originally or easily note, is this, is that these two forces cancel out. So that means this, our F net equals F of F. Okay? And we should also know that work equals F net, or F times D, or F net times D, however you want to call it. Okay? So you might say, oh my goodness, all I have to do is calculate FF. This FF is going to substitute into there. Whatever I got here is going to go here. And that's a good place to start. So the first thing you might want to say is FF equals mu Fn. This is from your reference table. And now I'm just going to take this value right here. I'm going to substitute it here. So mu Fn equals, or no, I'm sorry, times D equals W. So we're like, oh my goodness, we're making so much progress. Well, the thing we must easily see is this. Do we have any way of calculating D up here? All we have is mu. No, Mr. Shaw, we don't have it. What we do know is that our final velocity is 0. And we know that our initial velocity is going to be the one we found in part 1, which is 8.38 meters per second. But we don't have time or acceleration to find D. Now, we could find that. We could solve this FF. Remember, F net equals MA. We could try that, and we could solve for, F net equals MA. So how could we find this? Well, we could find FF because that's what we have. We could substitute in M, so we could divide both sides by M, and you could get A. Okay, okay. So we're going somewhere. And then you could say this. You could go, if you've got A, and you've got, let's go down a little bit, VF, and you've got VI, you should be able to find D. This is my acceleration. You should be able to find D. Okay, you can find that. That would not be too bad. That would be an easy way of doing it. Well, not an easy way, but it's a long, kind of drawn out way. It would be fun. It would be fine. It would give you an answer. And the answers might not actually give you the same one, because I have another technique, guys, and I want to show you my other technique. All this is fine, and all this shows a lot of thought and a lot of intelligence, but there's another way to find work. So let's go back and think about this. Remember, work equals change in energy. And in this case, we're talking about our objects moving. So it's going to be our change in kinetic energy. So work is going to equal KE F minus KEI. Now it says how much work is done by friction to bring the gazelle and tiger to a stop. Well, if these guys come to a stop, what's going to be our final kinetic energy? Well, anything that's stopped, you should immediately say kinetic energy is 0. So now, all we know is this, is work equals negative 1/2 m vi squared, where the thing important to realize is I'm talking about these two objects stuck together. So this mass right here, it's not just the mass of the gazelle, it's not the mass of the tiger. This mass, just m, equals m, come on, you can write now, mg plus mt. So you can now say this. I'm going to combine this into this. I'm going to say work equals negative 1/2 mg plus mt times vi squared. And what's my vi, guys? I had it up here before. We can go all the way up. The vi is going to be, and it's strange, but it's going to be our vf from here before. It's going to be this value right here. Now, the way you have to think about this, guys, is you have to think about things as a story. This is where physics really connects to English. Where, like, the first part of the story, the gazelle has no velocity. And then it gets tackled by the tiger and it's given velocity. But does it keep that velocity forever? No, we have this third part of the problem talks about the gazelle and the tiger losing their velocity. So they start off with what they had in the previous section, the 8.38 meters per second. But now they reach a place that we're on a frictionless surface. Then they reach a place that does have friction. So they lose that energy. They lose their momentum. And they lose that work is done by friction to change their energy. Okay, guys. Go Giants. Have a good Sunday. See you tomorrow.